Hello everyone, I am Brigurishi Mishra from IIT Bombay, and this is the online session of elements of solar energy conversion for week 7. So, in this session, I'll solve a question uh, for a flat plate collector. Okay, so this is I took from Sukhatme book. So yeah, this question I took from Sukhatme book. So the question is, a flat plate collector is made up of a copper absorber plate, copper tubes fixed on the underside, and one glass cover. Okay, so this is a fixed flat plate collector. So in this week 6 and week 7 we have like talked about the flat plate collector and the properties, how to calculate the useful heat gain. Okay, so this question, I think this question covers all the things whatever we have learned till now, like from the very beginning, calculation of incidence angle, calculation of total radiation incident on the flat plate collector, then the absorbed solar radiation, and then the flat plate components, like we have to calculate uh, the angle of incidence of beam radiation on the collector, the total solar flux incident on the collector, the tau alpha b and tau alpha d, which this calculation we have already seen in the last week's session, and then the incident flux absorbed by the absorber plate, the collector heat removal factor and overall loss coefficient, the water outlet temperature, and the instantaneous efficiency. So these 7 things we will calculate based on the data given for the flat plate collector. So I'll start with the first one. Okay, the angle of incidence, the angle of incidence of beam radiation on the collector, flat plate collector. Okay, so if you recall, we need to have the declination angle, latitude of the location, hour angle, to calculate the angle of incidence. Okay, so here the location of collector is given, it is Pune. Okay, the date is May 15, time is 12 noon. The collector tilt angle is given same, is equals to the latitude angle, that means in that case L equals to beta. Okay, the surface azimuthal angle is also given, AZ S is 0. Okay, so we need to calculate the first is to calculate the angle of incidence of beam radiation. So it is 15th May, so n will be 135. Okay, these things, since we have already calculated in previous online session, so I'll not give much time on this. If you have any doubt, you can ask, or you can check the previous online sessions. Okay, so now we can calculate the declination angle delta, which is 23.45 sine 360 by 365, 284 plus 135, and if you solve this you will get delta equals to 18.79 degree. Okay, now the IST, Indian Standard Time, is given 12 noon. However, we calculate omega based on the local apparent time. Okay, that means the solar noon of the local place, not the standard time. Okay, so this 12 noon is the standard time, and we have to calculate our angle based on the local solar noon. Okay, so for that we need to calculate the local apparent time. Okay, so local apparent time, LAT, is nothing but Indian Standard Time minus 4. There is this plus minus since Pune is in eastern hemisphere, so we are considering minus sign here. Okay, so minus 4, and then standard time latitude minus, sorry, not the latitude, it's longitude. Okay, it's the prime meridian. Okay, the meridian of the standard place and the meridian of the local plane, the difference. So standard time longitude, which is for India, it is Allahabad. Okay, and minus local time longitude, or the, yeah, local time longitude, uh, plus equation of time correction. So there is the formula given to calculate equation of time correction. I have already calculated it, so I am not again writing the formula for it. You can check the book or the previous lecture. So IST is given 12 hour minus 4, and standard time longitude, it is 82.5. Local time longitude, that is 73.85. okay, it's given here 73 degree 51 minute. If you convert it in the degree, it will be 73.85. okay, and this is in minutes, and this then equation of time correction is 2.6 minutes, so it comes 11 hour 28 minutes. okay, so now we have the local apparent time, we can calculate the omega. So omega will be yeah, 11 hour 28, okay, minus 12 hour, okay, and into 15, so it is 28 minus 28 minutes into 15, and since it is 15 degree for 1 hour, we need to divide by 60, so it comes around minus 8 degree, sorry, it's not 28, it's 32, so it comes around minus 8 degree. Minus, since it is in the morning, if you remember the sign convention, for morning omega is considered negative, for afternoon omega considered as positive. okay, afternoon means after 12. So now we have all the values. That means the azimuthal angle, surface azimuthal angle is 0 degree, and beta is same as the latitude, it is 80 degree 32 minute. If you convert this, it is around 18.53 degree. okay, so the cos theta, if you remember the formula, it is sine delta sine L minus beta plus cos delta cos omega and cos L minus beta. So here L minus beta will be 0 since latitude and tilt angle both are same. So if you solve this, you will get theta equals to 20.36 degree. okay, so we have solved the first one. Now the second one is total solar flux incident on the collector. okay, so total solar flux, so if you remember the formula, if we consider the isotropic model, considering isotropic sky model, IT is IBRB plus ID 1 plus cos beta by 2 plus I rho g 1 minus cos beta by 2. Okay, now this RB we need to calculate. So RB is nothing but cos theta, means here theta t, that is for the tilt angle. Okay, cos theta t by cos theta z. So we have already calculated cos theta t, we need to calculate cos theta z. So it is cos 20.36 is 0.9375, and if we write for the formula for cos theta z, I am writing with the values sin delta sin beta plus cos delta cos beta and cos omega. Okay, so if you solve this, you'll get RB equals to 0.9458. Okay, and from the data, the IB is given as 725 watt per meter square, ID is 230 watt per meter square, and the surface reflectance, reflectivity of the surrounding surface 0.2. Rho g is also given here. So we have all the values. So if we put all the values, okay, here I is IB plus IT. Okay, so IT will be around 914.7 watt per meter square. This beta is also given, so we can easily calculate 1 plus cos beta by 2, 1 minus cos beta by 2, and this I is simply IB plus IT. Okay, so this way we can get IT, which is 914.7 watt per meter square. Now the third one is tau alpha b and tau alpha d. In last class we have explained it in a detail, so I'll calculate these values not in very detailed. Okay, so tau alpha b and tau alpha d. So here B for beam radiation and D for diffuse radiation. So if you remember from Snell's law, we have n1 sin theta 1 equals to n2 sin theta 2, and we have already calculated here theta 1 is the incidence angle, which we have already calculated. Theta 1 is this 20.36 degree. So and n1 is air, n2 is the glass, which refractive index is given here. Refractive index of glass to air is 1.526. This is n2, or you can say n2 by n1, since it is given relative to air, n2 by n1. Okay, so we have all the values. We can calculate sin theta 2 equals to n1 by n2 into sin theta 1, so which is 1 by 1.526 sin 20.36 degree. If you calculate this, theta 2 will be 13.18 degree. Okay, so theta 2 is given. Now we have theta 2, so we can calculate the reflectivity for the two modes. So if you remember, in last class we have discussed that there will for the each solar radiation is nothing but the electromagnetic radiation, so it has two modes. Okay, two polarization mode, one T wave mode and one is TM mode. Okay, so the row first is sin square theta 2 minus theta 1 by sin square theta 2 plus theta 1, and if you put all the values, it comes 0.0512. Similarly, row second is tan square theta 2 minus theta 1 by tan square theta 2 plus theta 1 equals to 0.0361. See, these questions is very lengthy, but it's not very complicated. Okay, all the values are given. You just have to use the formulas to calculate the quantities step by step. Okay, you need to follow the steps. Like you cannot calculate the total radiation before calculating the theta and you cannot calculate theta before calculating the omega or the local apparent time. So it's just lengthy, but it's not very complicated. Okay, you just need to know the right formula to calculate the values. So now this way we can calculate tau r first, which is nothing but 1 minus rho first by 1 plus rho first, and here we have one number of covers, so m will be 1s, otherwise it would be 1 minus rho by 1 plus 2 m minus 1 into rho, where m is the number of covers. Okay, so since we have one cover here, so it is 1 minus 0.0512 by 1 plus 0.0512, and it comes around 0.903. Similarly, tau r second is 1 minus 0.0361 by 1 plus 0.0361, so it is 0.930. We have tau r first, tau r second. We can calculate tau r, which is the total transmissivity considering reflection only. Okay, so tau r is the average of these two quantities, so 0.903 plus 930 upon 2, and it comes around 0.9165. we have tau r, we need to calculate tau v, that means transmissivity considering absorption only. Okay, so for the tau v we need to know the extinction coefficient and the thickness of the glass. So if you see the data, the extinction coefficient of the glass is given 90 in per meter, this is K, and thickness of glass cover is 4 mm. Okay, so this is delta G, and since we have one glass cover only, so we can calculate the tau v very easily. It's nothing but the exponential of minus K, which is 19, okay, into delta, and here delta is given in mm, 4 mm, so we need to convert it into meter. Okay, since K is given in per meter. Okay, so 19 into 0.004 mm, and now since it is not the normal incidence, there is division of cos theta 2, and theta 2 is 13.18, which we have calculated already here. So if you solve this, it comes around 0.925. so we have tau r, tau v, we can calculate tau, it's tau r into tau v, and it is 0.848. okay, now we need to calculate rho d. Rho d means the reflectivity considering the reflectivity for the diffuse radiation. So for that we need to calculate for diffuse, we need to consider theta I is 60 degree. Okay, so if you calculate theta I equals to 60 degree, you can calculate rho d very easily. And if you remember in the last class, we have calculated for the two glass cover what is the rho d when there are two glass cover, and it turns out around 23.51. and if you follow the same procedure with theta equals to 60 degree, you can calculate the rho d, okay, which is nothing, so rho d is nothing but tau v into 1 minus tau r. Okay, and it will give the 0.144. so this is the standard value for a single glass cover. When there are two glass covers, it is around 0.21 or 23. okay, so rho d equals to 0.144. and also for the diffuse, so this is for the beam radiation. Okay, and we also have to calculate the transmissivity for diffuse radiation. So again, following the same way, we can calculate the tau d, which is around 0.768. okay, the transmissive, this absorptivity or transmittance due to absorption won't change, it will remain 0.925 for the both values. Okay, So now we can calculate the tau alpha b and tau alpha d. So tau alpha b is uh, point tau into alpha, which is 0.848 into 0.94, okay, divided by 1 minus 1 minus 0.94 into 0.144. This 0.94 is the absorptivity of the glass cover, which is given here, okay. Yeah, this one, plate absorptivity for solar radiation, this is alpha, okay. So alpha is given in the question itself, so that is why this since it is tau alpha by 1 minus alpha into rho d, so this is the formula. So it turns around 0.804, and in the same fashion we can calculate tau alpha d, which is, and for for the diffuse radiation, tau is 0.768, so it is 0.768 into 0.94 by 1 minus 0.94 into 0.144, and it turns out around 0.728, okay. So this fashion we have calculated tau alpha b and tau alpha d. So now the next one is the incident flux absorbed by the absorber plate, okay. So this is I think 5. The incident flux absorbed by plate. So incident flux absorbed by plate is nothing but the useful radiation, okay, which is S. So S is given as if you remember the formula, I had written somewhere here, okay, anyway. So S is, so IB, okay, IB into tau alpha b. So we have the values of IB, which is 725 watt per meter square and 230 watt per meter square. So S is just a minute, yeah, the formula for S is IBRB tau alpha b plus ID into 1 plus cos beta by 2 tau alpha d plus I, which is nothing but IB plus ID, IB plus ID, and into 1 minus cos beta by 2, and again tau alpha d. So we have calculated all the values. IB, ID is given, we have calculated RB, tau alpha b, okay. So in this fashion we can calculate S equals to so IB is 725, RB is 0.9458 we have calculated, tau alpha b is 0.804 we have calculated, ID is given as 230, and again 1 plus cos beta by 2 comes around 0.9441, tau alpha d is 0.728 we calculated, and again I is 955 into 0.0052 into 0.728, so S is 718.0 watt per meter square, okay. So this is the radiation absorbed by the plate. So if you can see, this is the radiation we are getting, okay, which is 914.7 watt per meter square, and this is the radiation which plate is absorbing. So there is a loss, and this loss is around around 200 watt per meter square. So that is kind of huge loss. If you increase the number of glass cover, maybe this loss is reduced, which we have seen, okay. And we will also see some questions on it, how the number of glass covers affect, okay. So now So I think this one is the fourth one, not the fifth one. Okay, so now the fifth one is the collector heat removal factor and overall loss coefficient. The collector heat removal factor and overall loss coefficient. So this is the tricky one. In most of the questions the overall loss coefficient is given, as if you remember the formula, the collector heat removal factor and overall loss coefficient are kind of dependent to each other. Okay, so if you know the overall loss coefficient, then only you can calculate the heat removal factor, else you cannot. Okay, so the either in the formula itself overall loss coefficient is given, or you have to do the iterative process to find out the overall loss coefficient. Okay, so iterative means first you have to assume certain number, certain value of the overall loss coefficient, and then based on that you can calculate the heat removal factor, the temperature of the different covers, then plate mean temperature, and then based on that you can calculate the total loss, and from there you can calculate again the UL, and which is overall loss coefficient, and if it is not matching with the value which you have assumed, then you have to follow the same iteration again. Okay, so that is a whole iterative process given in the example in a book Sukh Haath Mein Nayak. So that example is I think example 4 or 5, I forgot. Oops. So I think that is yeah, example 4.2. Okay, example 4.2 is given where you can check how the iteration involves to calculate the heat removal factor. We will show you the first iterative process, but we cannot go in that much detail. So just a minute. Okay, so so iterative procedure we have to adopt. Okay, so first iteration, so first iteration we need to consider some value of UL. So assume UL equals to 4.0 watt per meter square per Kelvin. So you so how can we assume any arbitrary value? So based on the experience and based on the like based on the data of the collector plate. Okay, since for this case the there is only one glass cover, and the absorption of the plate is also given 0.94, and we also got that the absorbed plate useful solar radiation absorbed by the plate is 718. So based on such data and based on the experience we can assume that UL assumption of this UL value is a decent one, and we will see how far we are from the actual value. Okay, so UL is given. Now we can calculate the M is root UL by K delta. Okay, and this K is the thermal conductivity which is given here. This is the K, no sorry, not this K. Okay, it's yeah, this one, thermal conductivity of plate material K. Okay, so this is given K, and we also have the thickness of the plate, which is not plate, the glass cover, which is around 50, yeah, 0.15, yeah, the plate of thickness, so delta plate thickness, okay, 0.15 mm. So from these data we can calculate the m, and it comes around, so 4 by 350 into 0.15, it is in mm, so we have to convert it into the meter, since K is given in watt per meter per Kelvin, so it turns out 8.73 per meter. Okay, so then we have to calculate the fin efficiency. Okay, F, so F is tan hyperbola m w minus t by 2 by m w minus t by 2. So to calculate tan hyperbola of x, we can use the formula of e to the power 2x plus 1 by e to the power 2x minus 1. I guess this is the formula. Let me just check. Yeah, sorry, it is e to the power 2x minus 1 here, plus 1 here. Okay, so in this way we can calculate the tan hyperbolic function. So if you calculate the fin efficiency, it turns out around 0.433, sorry, not 0.433, it's 0.942. If it is if you convert it in percentage, it is 94.2%. okay, and that's a very decent fin efficiency. Now we can calculate the f dash. F dash is the collector efficiency factor, and the formula is given as 1 by ul divided by w 1 by ul d plus w minus t into f plus 1 by cb plus 1 by hfi pi di. Okay, since in the question itself it is given that bond adhesive resistance is negligible. Okay, adhesive resistance is the bond resistance cb here, so we can say that 1 by cb tends to 0. okay, so we can neglect this 1 by cb, and now w is given, which is here, this is center to center distance, so this is w, inner diameter of tube, which this is di, and outer diameter of tube, which is d. okay, so we have d, di and w. And hfi, this is fluid to tube heat transfer coefficient, so this is hfi, fluid to tube, okay, heat transfer coefficient. So we have all the values, so we can calculate the collector efficiency factor f dash, and it is around 0.901. okay, so we have the this value, and now we can calculate the collector heat removal factor, which is m dot. So you can see all the things are connected. Okay, you cannot calculate fr before calculating f dash, and you cannot calculate f dash before calculating the fin efficiency f. okay, so we are just using the formula to calculate the values step by step. So fr is m dot cp ac ul 1 minus exponential of minus ac ul f dash by m dot cp, and if you put all the values, it turns out, so m dot is the mass flow rate, okay, which is given here, water flow rate m dot, and AC the collector area. So this is the length of absorber plate, width of the plate, so this gives the AC. okay, so we have all the values, so we can calculate it, and it turns out around 0.863. okay, so useful heat gain, we can calculate, since we have the FR, so we can use the most useful formula to calculate useful heat gain, which is QU dot equals to AC into FR S minus UL TFI minus TA. Okay, TFI inlet fluid temperature, which is given here. This is TFI, okay, and ambient temperature is given, which is TA. So in this way we can calculate all the values. We have this FR, S, UL, TFI, all the values. So QU dot turns out 977.7 watt. Okay, now we have QU, so we can calculate the loss. What is the loss term? This is the loss term. Okay, if you remember the formula for the loss term, it is a UL. If it is not FR, okay, if heat removal factor is not there, then this is the loss can be calculated as UL TPM minus T. Okay, and that is QU dot minus this quantity AC into S. Okay, so loss can be calculated as loss. What is loss here? So loss is nothing but UL into TPM, which is the mean absorber temperature, the mean temperature of the absorber plate. Okay, TPM minus TA, and into AC also, into AC, and which is equals to so AC into S minus QU dot. Okay, so we have all the values. We have AC which is 2 into 0.98, and S is we have calculated 718, and Q dot we just calculated 977.7. so from this we can calculate the loss, which is 429.6 watt. And here we have UL, we have AC, we have T, so we can calculate TPM. Okay, so TPM, I'm writing it in Kelvin. Okay, so TPM is 353 Kelvin. So we have TPM now. So now we can use this TPM to calculate top loss coefficient, since we can easily calculate the side loss and bottom loss coefficient. So for the bottom loss coefficient, the data is given, the insulation, the thickness of insulation, and the insulation conductivity is given here. And also for the bottom loss, it is, for the side loss, it is given that assume that side loss coefficient is 10% of the bottom loss coefficient. So we can easily calculate side loss and bottom loss. The only problem is with the UT. Okay, that is the top loss coefficient, and if you know that UL is nothing but UT plus UB plus UE. Edge means side. Okay, so either you can use UE or US. In some books it is written side loss coefficient, in some books it is edge loss coefficient. Okay, so if you remember the lecture, UT can be calculated as 1 by R1 plus R2. Okay, yeah, from plate to from absorber plate to cover plate, and then from cover plate to sky. There are if there are two plates, two cover plates, it is R3 also. Okay, so then so now here then it comes the iterative process. So again you can use this TPM to calculate R1, R2, R3. There are some analytical expressions, numerical expression given to calculate this R1, R2, R3. So I'm not going into that detail. You can check example 4.2 of Sukhatme and Nayak book. Okay, so after doing this 2-3 iterations, it turns out that UL is around 4.995 watt per meter square per Kelvin. Okay, so this is the UL, the final value of UL. So if you see, we have assumed UL is 4 and it is 4.995. So this is the decent approximation which we have considered. Apart from this iterative process, there are several numerical expressions given to calculate the overall loss coefficient of the absorber plate. That too has a certain limitation, but in that limitation it works very well. Okay, so you can check the several textbooks or even the journal paper, what are those expressions for the UL. Generally UL is given, but for the real life scenario you have to calculate the UL, okay, based on this iterative process. So now we have the actual UL, we can calculate the M, which is again root UL by K delta, and it comes 9.754 meter inverse. And then we can calculate the fin efficiency, which is it turns around 0.9285, and then we can calculate the collector efficiency factor. The same process here, we have already given how to calculate this, so I'm not calculating it again. Okay, the process is same, it just now we have the right UL, so we can calculate M using this formula, then F dash, then F using this formula, then F dash using this, and then heat removal factor using this formula. Okay, so F dash is if you put all the values, then F dash is 0.8794, FR is 0.8344. okay, and now we have the value, so you can calculate useful heat gain. It is AC FR S minus UL TFI minus TA. Okay, so putting all the values, it is 888.3 watt. Okay, so we have this, so we can also calculate loss, and loss is AC into S minus QU dot. It is so AC is 2 into 0.98 and S is 718. We have calculated QU dot, we just calculated 888.3 watt, so it turns out around 518.98 watt. Okay, so and loss is nothing but UL into AC TPM minus TA. So you can calculate TPM is 351.2 Kelvin. This is the average temperature of the absorber plate. Okay, so we have calculated all these values. Now the next one is we have to calculate the water outlet temperature. Okay, so the water outlet temperature, so the sixth one is water outlet temperature. Okay, so water outlet temperature we can calculate from the heat balance equation, since we already know the useful heat gain from heat balance equation. It is M dot Cp TFO minus T5. FO means output fluid, Fi means input fluid, equals to QU dot. So M dot is given 70 kg per hour. Okay, Cp is 4.18. okay, and TFO minus TFI is 60. Now here QU is given in watt, so we need to calculate in, since this Cp is in kilojoule per hour, so we also need to calculate QU in kilojoule per hour, or like yeah, we need to modify the QU unit so that the unit of left hand equals to unit of right hand. So for this it is 888.3 into 1000 to convert it into kilo by, sorry, not 1000, so 3600 to convert into per hour divided by 1000 to convert it into kilo. Okay, so if you solve this, you will get TFO equals to 70.9 6.93 degrees centigrade, which is 344.1 Kelvin. So if you know the TFI is 60 degrees centigrade, and you are given TF, you are getting TFO 70.93 degrees centigrade. So there is an increase of temperature difference at around 10 10.93 degree. Okay, if it is operating from morning to that the time which is given. Okay, okay, since we are calculating all the calculation for that particular time. So now the next one is instantaneous efficiency. Instantaneous efficiency. So instantaneous efficiency is nothing but the useful heat gain divided by the total energy hitting on the surface. So here this A is not the area of absorber plate, but this is the area of liquid flat plate collector. Okay, and we have the values of Q dot, which is 888.3. Now for the area of collector, the dimensions is already given here. Okay, this is length of collector, width of collector, this is A. So in this way we can calculate so 2.08 into 1.07, and the IT is 914.7. so it is around 0.436. that means the efficiency, instantaneous efficiency is 43.6%, which is a quite decent efficiency. Okay, so yeah, that's it. So this, in this question we have calculated, like we have analyzed the heat removal factor, overall loss coefficient, and the instantaneous efficiency of the flat plate collector, whose location is Pune, and the date and time is May 15, 12 noon. Okay, so we have used all the information which we have gained till now from this lecture. So that means the calculation of angle of incidence, the calculation of total solar flux and the on the tilted plane, and then transmissivity, absorptivity of the flat plate collector. Then we calculated the total whatever the useful radiation absorbed by the absorber plate. Then we calculated heat removal factor and overall loss coefficient using iteration. I have only shown one iteration. Okay, and then based on the values we obtained, we calculated the water outlet temperature, and we observed that it is giving the temperature difference between inlet and outlet is 10.93 degrees centigrade, and the instantaneous efficiency is 43.6 degree 43.6%. Okay, so yeah, that's it from my side. If you have any question, please ask. Okay, so no question, so I'm stopping the recording here, and I'm also stopping this session. So we will meet on next Friday. Thank you.